Alright, this week let's look at LSDyna. Damping is LSDyna. Basically, I'm gonna look at a few different damping options and so also look at what not to do because these damping options can sometimes give you really bad results. Like what you have right here, you can sort of see how in this case, because it's over damped through a mass damping, you actually have the block appear to be way heavier than it actually is, which is completely incorrect. So this is something we want to sort of pay attention to. Okay, real quick agenda. So I'm gonna review the basic principles behind it, and then I'm gonna look at a couple options for massive proportional damping, and then I'm gonna look at a couple options for the stiffness proportional damping. And then we'll look at a couple different examples to sort of looking at it as sort of as a background, and then we'll look at the risks and pitfalls for these damping options. Basically, what happens if you over damp it. Okay, so a basic overview, obviously, damping is just a way you can sort of lose energy in a dynamic system. You can either under damp it, over damp it, or critically damp it. That just depends on how quickly the oscillation dies down. As you can sort of see, this is a pretty basic overview. Now, in terms of the different damping option in Dyna, we're gonna look at damping frequency range, which is a way to damp the entire system based on a frequency range. A constant damping is applied inside this frequency range, and outside it, you have a sort of an attenuating effect where the damping gets a little bit lower and a little bit lower the further away you are from the range. The way this damping works is that you can actually damp out rigid body modes, and it could introduce. It actually does not. If you use the deform option, it does not damp the rigid body motion. But if you use the standard option, it does damp out rigid body modes. So these things are really important to know if you're applying some kind of rigid body motion or boundary prescribed motion inside a model. That sometimes you're gonna get, say, a high reaction force, or the rigid body motion itself can be reduced, as I will see in a second. Now, depending on how far the ratio of F high to F low is going to be, you can this option also increases or decreases the dynamic stiffness. Basically, it shifts your natural frequency up and down, depends on which option you're using. So that's something to pay attention to. But basically, if we use a very small amount of damping and keep the range relatively low, you get a decent. You basically don't introduce a lot of error into the systems. This is a quick summary from the documentation, as you can sort of see basically what I summarized. I think usually if you use the deform option to damp out certain vibrating structure under load, this usually does a pretty good job. But if you have, especially if that's the case, if you don't have any rigid body motion, like for example, you have a solid, rigid tool that's sort of deforming things, or things are rotating, for example. But otherwise, you can use a standard option, which allow you to damp out rigid body motions if needed. Okay, and then you have the mass-based damping, which are the damping global and damping par mass. These two damping cards basically add a damping force to damp out the acceleration in a body, right? So this is the type of damping that can add a lot of artificial weight to a structure, because you're adding the additional force term to achieve the same amount of acceleration. It's almost the same as actually changes the mass of your system. So the standard rule here, based on documentation, is that you want to make sure your value of your damping here is about 2 times your lowest frequency mode of interest, which is the first mode of interest from a modal analysis. If you don't, like for me, something like this, right, is I'll use a very small number to start, unless I want to do a modal analysis first to see it. But something like this is very important that you don't damp out a rigid body motion, as I'll demonstrate in a second. In terms of stiffness damping, this is the basic, numerical Rayleigh beta damping. Basically, it allows you to damp out analysis based on the stiffness of the system. Essentially, if you use a negative coefficient value here, this is the coefficient here, it's used for implicit analysis. Otherwise, you use that for an explicit analysis, right? And then the actual value of beta usually is between, like, I think it's like 0.1 or 0.3 or something like that. But basically, you want to keep the number relatively small. And then if you do that use for explicit analysis, you want to sort of adjust your TSS factor a little bit as well. Usually you make your TSS factor a little bit smaller. That usually helps a little bit for stability reasons. Okay, let's look at an example, which is the easiest thing to see with examples, right? This kind of problem, very simple to see. So this is the basic beam problem. You can sort of see this is the one that basically I deform a beam in the beginning. until it reaches here. Then I let that deformation go, and you get this oscillation that happens. And what you have here is a damping frequency range at a value of 2%. So you can sort of see there's a slow attenuation, dies down over time. This is a basically under damped system, right? But this is the kind of thing that you can sort of see to over about 0.2 seconds total analysis time. So using this value, you basically changes the dynamic stiffness of the system, but you also allow the energy dissipation to occur. Right, and then what you have for the other option is that if you use a mass-based damping, you can sort of see it basically just flatten out right away. And if you use the undamped system, you basically have oscillations continuous on. And I can show it real quick inside the actual system within the LS pitfalls, which I prepared, right? So what you have here, hold on, I need to make sure I adjust the yeah, I have a lot of window open, sorry about that. So let's just see if we can, so this one will be undamped. So I think this one is the sort of underdamped, right? So what we have basically, you have the arm deforming, and as soon as it releases the force, it just goes back to the beginning because it just basically overdamped. Over here you have a system that's slightly underdamped. I think I'm over here. And let's go ahead and add a timeline. In this case, I have an oscillation that damps out like this, right? And I can also completely undamp it. If it's completely undamped, I'm basically in this graph right here. Make sure my timeline is selected, and you can sort of see this is when it's undamped, right? That's a very standard type of problem that we can look at. Basically, depends on the amount of damping you add. You adjust the dynamic stiffness of the system, but it also allows you to apply a certain amount of damping. So for a problem like these, right, you can just apply stiffness-based damping, or even you apply mass-based damping as long as the number is adequate. You don't over-damp it, and we're okay. And you can see we get the same amount of overall deformation under the same amount of load. So it gives you the relatively correct response over time. All right, now if we do a dynamic problem in explicit, where we have a plate hitting a ball, right? So this is a complete undamped system, as you can see right here. Now, if I want to damp out this kind of vibrations, right, you can sort of see you can easily over-damp the system. So for example, something like this, right? You can see my total deformation is actually smaller than before. If you look at the previous graph, it goes up to about 0.3, right? And over here, you basically lose a lot of amplitude in that deformation because the damping that occurred in the system. Now, in reality, right, this type of damping is mostly stiffness-based. But what we're doing in the simulation side is that we're adding a numerical damping, which is something that's essentially based on a guess. So in most cases, you want to use a number that's as small as possible. In this case, I use a mass damping of 200, which is also a little bit over damping the system. You can sort of see. And then you can sort of see the different other options that I tried just to get a sense. So for example, instead of using 200, if I use 20, then you get a much less damped system, right? It's much closer to the undamped situations. If I use a frequency range of 5%, you basically over damp it, right? So for a problem like these, you can almost run it undamped, right? If you don't care about the energy dissipations. But if you do, you want to use a very small amount of damping, right? For example, something like maybe 1%, right? Instead of using 5% might be a better option for this. So it usually requires a few tries to get the right amount of damping into the system, all right? And basically, if you over damp it, you actually lose out the amplitude of your reactions, right? So you don't just over damp the system, you also lose some amplitude because most of damping is applying a additional force term in opposition to the nodal velocity, nodal accelerations, for example. So if you over damp the system, you also lose the peak amplitude, which sometimes is what you're looking for. All right, now if we look at the airbag problem, this is a problem that I ran into last year, right? Basically, if I were to apply airbag, pressurize it, and then to hit it against a wave in a purely undamped system, you can see how the airbag pressure eventually raises the ball up, or raises the block of mass upwards, right? And that's when the pressure applies that load upwards to push the block up. Okay, but if I was to use a global damping of 1000, right, you can sort of see it made the block artificially heavier. Even though I killed a lot of the vibration in the system, I actually lose the entire physics of the problem because I apply way too much damping here. Right, so for something like this, as a mass damping, you want to apply an extremely small number. So you really can't just use some random number without really looking into it. Some number, like in this case, it has to be a very, very small number. And if you look at a stiffness-based damping, in this case I use a stiffness-based damping, you can sort of see in this case the damping is much more realistic, right? So instead of using mass damping, which damps out rigid body mode, you want to make sure you use a stiffness damping, which does not damp out rigid body mode. And that's the type of thing that we can do. The stiffness-based damping, which is an option especially for like the damp frequency range deformed up there. Use this option right here. The damp frequency range, either deform option down here, is the best option to use for cases like these. Okay. All right, that's basically the whole thing. It's going to be a very quick week this week, and you can sort of see the different type of response. This is undamped. This is completely overdamped. This is sort of slightly underdamped. You see the underdamped system is a much better representation of the overdamped system. So this is the type of thing that you want to do with damping. Now remember, right, damping is a pretty easy concept to understand, but it's actually pretty difficult to get it right inside a real model. So in most situations, I like to just underdamp it, because if you overdamp the system, you basically completely ruin the analysis, right? Such an example with this airbag right here, for example, right? So we want to sort of damp just a little bit to reduce some noise. If you can live with completely not damping the system, then don't damp it at all, because that actually does a much better job in a lot of ways, where you don't lose any accuracies. I think any damping we add is also always going to be a little bit of a guess, and if you over damp it, you can ruin analysis. And that's why I think that the takeaway from here is to underdamp the system as much as possible. Use a very small damping coefficient in all of the damping cards that's available. Oh, I should mention that these two cards I didn't talk about, these are for frequency domain problems. Which when I do these, I'll show them. But the overall concept is the same. We want to be very careful with what damping coefficient we're using for each of these options, right? The documentation made it pretty clear on what we wanted to do. Okay, thank you very much.